that's where we stopped last time. All right, we spoke about phasors. We talked about how we go from a time domain to a phasor domain. And then, so I'm going to continue after that and try to talk about the fundamental equations, voltage and current on a transmission line. Because before I continue, do you have any questions on the material we covered last time? So I don't hear any questions. Then I will assume that if you have any, probably I will remind you as I'm going through the material. Okay. What we did is the following. Just to remind you, we started with a real microstrip line. All right, it was ground, and then there are traces on top. A line that is made out of one trace and ground underneath it, and is separated from the ground by a dielectric, is called a microstrip. This is a fundamental line. Most of it you will see used in most circuits, even if the most updated circuits like what you're gonna see here, if you were to open one, and then you could observe it. If you have an old iPhone, before you return it, you can open it. It's not a bad deal. They're gonna take it the way it is. So you can see exactly how the lines look. There are most of them microstrip, and in some places you will see some other things. But there are, of course, when you go to lines, there is not only one. Over the last 20 or 30 years, people have looked at different types of lines. But the characteristic is the following. In all of these transmission lines, there is one characteristic, that they are made out of two conductors. The conductors can be a microstrip like we had here before in the beginning, like this. It could be something like that. Or the conductors could be two strips like this, one next to the other without a ground underneath it, or two strips, one next to the other with a ground underneath it. Even if in reality they don't use the ground, they are two strips like that. Or three strips, two grounds on the side, and then one strip in the center. Different kind of things. This is called the coplanar waveguide. They do different things, but the fundamental thing, they behave a little differently. The fundamental thing is that the way the fields are excited and create a voltage and a current, which is what we use in circuits, those voltages and currents, they go exactly the same way on these lines as they go in microstrip. Maybe the fields do not distribute exactly the same way, but in terms of voltage, that applies across the conductors, or like between the top conductor and the ground, all right? And the current that flows in the conductors, they, along the length of the conductors, they behave the same. So even if we started with a microstrip, we created a symbolic representation, which I have here, which is good for any type of transmission line, because any type of transmission line has two conductors. Now, even the one that I said with three, the outer two is ground, so you can think that the ground wraps around, all right? So one ground, one strip line. Could be two strip lines, one of them is ground, the other is a signal line. Or it could be the ground underneath and the signal line here. It does not matter how you put them in space. The bottom line are two. One signal line where the signal goes, and the other path where the signal comes back. You can see it here, the current in green. All right, it goes, the top is where it goes from where it's excited to the other end, and the lower is the return. All right, so now from there, last time we explained why we created a circuit representation that looks like this. That is, from a microstrip, from a physical, we went to symbolic. From symbolic, we are going to a circuit. The difference in the symbolic representation is the following. The symbolic representation still has one geometrical parameter, and that's the length of the line. All right? So, what do I mean? In the physical representation, all of the geometrical parameters are there. Everything is there, fully described. But then I go from the symbolic, from the real representation here, to the symbolic representation that I have here. And I have just two straight lines and only one dimension. And that dimension is the length. And I call it Z. So from a three-dimensional problem to one-dimensional problem with a symbolic representation, but there is still one dimension there. And from the symbolic representation, we go to the circuit representation that has no lengths, no dimensions. When you did circuits in 214, everything was like there is no length of line that causes any change. That's what I mean. All of the lines, the currents flow, the voltages are there, unless there is a resistor or another element, there is no change in the current, there is no change in the voltage. That's what it means. In reality, you may have a circuit that covers the whole page, that covers the whole wall here behind me, and still is going to be considered to be like one dot in a 3 dimension. There are no dimensions there. So we go from 3 dimensions to 1 dimension symbolic to 0 dimensions in the circuit representation. However, see how we do it so we don't lose information in the process. So we have, in the symbolic representation, we take a section of the line, and we assume that this section is very short, and we call it DZ, and it's here. And then we have a line that starts at A prime, and I need to put the prime here, so it somehow got lost, and the BB prime on the other end. That's sense. And now we replace that with a circuit that still starts at AA prime, it ends at BB prime. There is no length involved physically in those wires. However, look what I've done. I have a resistor, and we talked about this resistor because it comes out of the ohmic wires, all right, or in the conductors. So this resistor, however, I multiplied it by DZ. Why? Because the resistance we found before in our circuits, and we talked about this resistance, the resistance for our lines is in ohms per unit length. So when I tell you that I have a microstrip line with this much ohmic losses, they will give them to you in ohms per unit length. So if you have any length, very short length of this line, the only thing you have to do is to multiply your resistance, which is in ohms per unit length, by that length of the line. In this particular case, is DZ. Then I do the same with L, with the inductance, LDZ. Then I do the same with the capacitance, CDZ. And I do the same with the conductance, GDZ. And here you see that I have already moved to the phasor domain. So I multiply all the inductances by J omega, all of the capacitances by J omega, even if I know that J omega L is an impedance and J omega C is a conductance. All right?
Why do you need a separate resistance and a separate conductance?
Because the resistance comes from losses in the wire, and the conductance comes from losses in the material that separates the two conductors. So in the microstrip is the dielectric substrate. All right, so imperfect dielectrics have losses.
Oh, okay. And those are represented as conductance?
Exactly.
Okay, okay, that makes
G
sense.
per unit, it's 1/ohm per unit length, the value of G, the units,
Okay.
1/ohm per unit length. And R is ohm per unit length. Now, there is another thing I wanted to also remind you here in terms of units. All right, so let me open a page here. So I will make a parenthesis and then I will speak a little bit about units. So R in this is ohms per unit length. So what that means is that I choose how to give it to you. I may choose, example, to give that to you in ohms. Say, for example, R is 10 ohms per meter. That's my choice. That's how I measure it. So for every 1 meter long line, I have 10 ohms. If I could give this to you in 0.1 ohm per centimeter. Okay. Now, G, RDZ, however, has units which are ohm. Okay, because I have multiplied with DZ. I may tell you that I have a length of line which is 3 centimeters, and I have a total R. This is the total R on the line. I have an R for this length that is 3 centimeters. If I had the same here, there is 0.3 ohms, for example. All right, so usually I give you the first R. I don't give you R multiplied by something. I usually give you per unit length. But in any case, so then also G is 1/ohm. You have seen that, isn't it? Ohm to minus 1 per unit length. Do you know how else we call the ohm to minus 1? Only engineers could do that, or scientists. Mo. Yes. So it's mo. The reverse of ohm. Only, I don't know who found that, but in any case, unit length. Usually you see it as, I like to show it 1/ohm. Then G dz is 1/ohm. Now, question. L is what? Obviously, Henry's per unit length. Now I have a question for you. What is omega L? What are the units for omega L? How would you think about this? Forget
That,
about that. Look at this one here.
is that like radial Henrys or something?
See, like, omega L practically is in ohms, omega L dz, because they are in the same. See, I have it like an impedance. Yes. The reactance, exactly. Yes, because it's a reactance, omega L is in ohms per unit length. And then how much is omega G? Ohms minus 1 per unit length. Or did I say? Yeah, omega C, excuse me. G. Omega C. Ohms minus 1 per unit length. Okay, that's what it is. So now you have all of the units, and so the same units, all right? So R and omega L give the same units as also the same G and omega C have the same units. So then I go from up here to the symbolic to the circuit. Okay, now we are in circuit representation. Now I can use Kirchhoff's laws. All right, things that we know. KVL, I apply it here. KVL says the following. First of all, what I observe, that if VAA prime is at Z and VBB prime is at Z plus DZ, all right, because still AA prime and VBB prime, they are separated in space. So along this line here, V of Z and at AA prime and V at BB prime are voltages, but one of them is a distance dz away from the other one. All right, they're separated because that's what happens in the symbolic representation. Now, we have moved out of the symbolic to the circuit, but we still have dz in there. All right, you see that dz is just multiplied the values of the elements. So VAA prime is at Z, then VBB prime will be at Z plus DZ. And the same thing, if IAA prime is at Z, IBB prime is at Z plus DZ. I also need to remind you of something here. And I will write it here so you can see it. If I have a transmission line, and I'm going to use a symbolic representation, all right? So I have this transmission line and this one, symbolic representation. And I start here and I end here. And then I say that I have, this is A prime, as I did before, B prime. And now I say that I have A prime to be at Z. And then I have B prime to be at Z plus DZ. How is V situated on this symbolic line? V goes like that. So V is a voltage between these 2 points. So say this V is like that, and I will show it like this, but this line really shows that from the positive end to the negative, there is an electric field line. And the electric field line, if you remember very well, is like confined between the 2 conductors, all right? In anything you have. The microstrip is gonna be between the top conductor, the strip, the trace, and the ground. So that is, and then V, therefore, at every point, is gonna go like this. And V at every point is gonna go like this. Okay, that's for V. V, therefore, applies between the 2 grounds, the 2 metals, conductors. How about the current in the symbolic representation? The current here, if I use a different color, at this point, this is IAA prime of Z, and then it's here, and then here, all right? So continues here. We don't consider terminating. We just think that it's an infinite long line, and we just consider a section of it, all right? So practically, the line by itself is gonna continue in this. So the line continues practically here, even if I have considered only a short section of it. All right. Now, the current, therefore, one current flows like that all the way. How about the lower conductor? What happens there? There is this return current, but I never show it. We all just know it. We know that in the lower conductor, there is going to be this return current. This return current is going to be always there, all right? Even if we're not going to show it, you're going to always show the top current, and then you know that underneath it, there is a return. All right, not like in circuits though, we show only the current that goes through the elements of the components of the circuit components, but we don't show anything that goes underneath it in the other, right? Unless we have to apply somehow, we have some other components, or we have to apply Kirchhoff's law for current there. So in any case, I just wanted to remind you that the voltage applies between the two conductors, the current flows like this, and there is the return current flowing under, but we never show it. Okay. Now, what we do here, we apply Kirchhoff's voltage law. So we say the voltage between A and A prime is nothing else but the voltage drop between along the resistor and the voltage drop along the inductor. So practically I write it like this. And this voltage drop is like this sum times the current that flows through, all right? So like J omega L is like another resistor, but it's an imaginary number. We are in phasor domain. You remember, you've done that. So you always treat in the phasor domain R and L like this. Plus, therefore, according to Kirchhoff's law, whatever voltage applies across C and C prime, the voltage drop across C and C prime is nothing else but the voltage drop across B and B prime. Do you agree? Okay, so we're here in parentheses. Okay, just a circuit. Now, then that is the voltage Kirchhoff law. Now then we go and apply KCL, Kirchhoff's current law, at point C. And what do we have there? That the current that flows, the AA prime of Z flows toward the node, and out of the node, they flow two currents, one like this going down and the other going like that, all right? You have two currents that flow. In fact, let me take that closer to the node, like here. So at that node, IAA prime Z of Z, which flows through this, all right, and arrives here, is equal to this current that flows out of C towards B, which is B prime, Z plus DZ, all right, plus the current that flows down through the parallel combination of G dz and J omega C dz. So practically, I have this equation from Kirchhoff's current law. All right? The current that flows into the node, I do it here like this. The current that flows into the node here, that current that flows in is equal to the sum of this current plus this one. And that current that flows here down is equal to this voltage across divided by the impedance, but multiplied by the conductance. That's where you have the voltage multiplied by the conductance. Okay? Otherwise, it would, if that were an impedance, we would have to divide. Okay. So now I realize also what I said, that VAA prime of Z is nothing else but the voltage that I have on my line here, you see, at point Z, and my VBB of Z dZ is nothing else but the same voltage at Z plus dZ. So they do belong to the same function. It's just that one, so if you have one voltage function of Z here, if you have one voltage for the line, then VAA prime is that voltage at Z, and VBB prime is that voltage at Z plus DZ. And that's what we realize here. And the same way, we say that if I have one current that flows down my line, like here, all right, one current, then practically, because the line does not, it's not interrupted by anything, then practically my current at A prime, according to this, is going to be equal to the value of this current and Z, and my current in B prime is the value of this current at Z plus dZ. So if I realize that and then I plug in those into these expressions, then what I get, and I have to, is something very interesting. I get here, of course, this expression by replacing. I get, first of all, this expression, and then I group the V's together and the I's together, especially the ones that have Z plus DZ. And then what I have here is this expression that has all of these V's on left and the I on the right, and this expression that has all of the I's on the left and the V on the right. And there I stop for a moment and I observe them. First of all, what you observe is that these two cancel, all right? And therefore, what else do you observe? What is this one here? Or this one? What does that remind you? What do you think that reminds you? A derivative. Do you remember here? Let's remember the following. df of t dt is nothing else but f of t minus f of, let me see, f of t plus dt minus f of t dt. Or you may have seen it like this, f of t1 minus f of t2 divided by t1 minus t2 at the limit when t1 goes to t2. And that is going to be df of t dt. Remember that? All right. I mean, if look at this just to confirm that this is exactly how we have defined the derivative. As a matter of fact, I think the most common definition of the derivative is this one. And then, however, some other times people show it as part of a limit. All right. So that is a derivative, which means that I can replace this one here with the derivative of v with respect to z, and in this expression, and this one here with the derivative of the current with respect to z. So I have now these two equations from above. These are called the Telegraphs equations. Remember I told you last time about telegraph? Okay, and the telegraph, the same guy, was very smart guy. He was able, without even knowing derivatives, you know that we did not have then this formulation for derivatives. People were writing, if you read the initial document that Maxwell wrote, everything was written by text. We did not have those mathematical symbols yet. Okay, so now we have these two equations. Then what do I do out of 5 and 6? I go to 5 and I differentiate it once more. Why do I do that? Because I want to get rid of the current. I want to find one equation for V and one equation for I.
Wait, that's supposed to be G plus JW, not or J omega L or J omega C.
See, thank you. Thank you, thank you. Yes. Okay, so then we differentiate this, the first one once more, and we get the d squared v of z dz squared is nothing else by this equation 7. And then by substituting into 7, equation 6, whatever I have from 6, all right, here, I'm getting this equation for v, all right? And this is called the wave equation, the wave equation. Now, have you seen something similar to that when you had LC circuits? And that is something here to remind you. Do you remember when you had an LC circuit? Because that's what we have here, all right? Even if I were to assume that we have 0 losses, so let me put this one here. Ah. Okay, put this here because that's where it's supposed to be. Now, what happens for 0 losses? 0 losses. How is this equation going to look like? Make that even smaller for a moment. Okay. So when we have 0 losses, and that's most of the time, that's what we're going to do in this class, 0 losses. What does that mean? Your R equals 0. And what is your G for 0 losses? Yes, thank you. All right, so this is extremely important to remember it. So when I have 0 losses, what happens to my wave equation? So wave equation becomes d squared v of z dz squared equals what? Minus omega squared LC v of z. All right?
How'd you derive that? Wouldn't this go to, wouldn't that go to infinity since the g is going to infinity? Just looking at the
Yeah,
equation.
the impedance is, excuse me, the impedance goes, the resistance goes to infinity, yes. So I was supposed to do something here. I made a mistake in this one. So the best way to write it is that 1 over G goes to infinity.
Okay.
All right, that's what I missed. Thank you. When you have very high losses, which means that your G is going to go to 0, the G itself, and then what you are going to have is that practically you have an equation like this. Now, don't get confused when I say G goes to 0, because I may show G as a resistor, but remember that G is a conductance. So all right, remember that. A lot of times you're gonna see G value next to a resistor that looks like a resistor, but in reality, G is a conductance. So if you were to go and combine the resistive component with the capacitive, the G will look like 1 over G. Do you see what I'm saying? So if you are correct, then you said it's open. It has to be open in the circuit, but the resistive element has to be open, which means that 1 over G has to be infinity. Okay, got it. All right, so now let me stay here for a moment and then remind you something. I want to go back for you for a moment, and then ask you. Um, you have seen LC circuits, have you? You have seen a circuit like that, which is only LC, like this. If I take away the resistance, the resistor, and I take away the conductance that I have, or the other resistor, if you like, the one that is in shunt configuration, then my line is going to look like this. Do you agree? LC. Okay. What happens if you have an LC configuration? This is what we have here. But another LC configuration you have seen is this one. Is that right? In circuits, a series configuration. And that is, what is this now? That's a question that I asked the other section, this one is a series configuration, the one that it's highlighted here with a circle. What is the other configuration? Neither. Thank you. It's neither of the two, all right? If people say I have a series LC, they mean this one. If people say that I have a shunt LC, they mean this one. All right, series, shunt. And in fact, I don't need this here. So this, you have seen the series and the shunt. And here now, you have this one, which is neither of the two, but it's an LC circuit. And what happens to LC circuits that you have, forget about the transmission lines. Remember, what happens when you have an LC circuit from circuits? They resonate, exactly. What happens, therefore, when they resonate? Okay. First of all, you have developed that resonant frequency. Remember, omega r is square root of LC. You say, whenever I have an LC circuit, it does not matter how it is connected. It does not matter. It can be with series, it can be in parallel, it can be something else. If it's 1L, 1C, then always that circuit resonates, and resonates at a frequency which is 1 over square root of omega of LC. This is what you've seen from circuits. First of all, I wanted to remind you, because we are going to see that later, and I want you to remember that. Okay, so what does this mean that the circuit resonates at that frequency? I will erase some things here. It means that for half of the period of the frequency is 1 over t. T is the period of the signal. For half of that period, if I'm showing here magnetic energy with this, if I start with all of my energy to be in the form of magnetic, and this circuit is connected, of course, it's not like this, has current flowing through whatever, so I have magnetic energy. For half of the period, this magnetic energy is going to change into electric, and for that period of time, it's going to move here, and it's going to become, at the end of the half period, it's going to become all electric. And therefore, it's going to be gone from there. It's going to be all electric at the end of the half period. And then what happens? Then goes backward. Then your electric energy now goes like this and transitions into magnetic for another half period. And at the end of the full period, your energy has gone from magnetic to electric and electric to magnetic, and then starts all over again. All right, and that's why we call it resonance. This thing is like a pendulum. All right, assume that you have a pendulum that is moving. On one end, it has all magnetic energy. It moves down. On the other end, it has all electric. And it moves down, all magnetic. And it moves down, all electric. And it does that for like every half a period, goes from magnetic to electric, from electric to magnetic. And then that is the resonance. That is the resonance. Now, in circuits, that happens all the time when you hit that frequency. You know what is the good thing about transmission lines? That this frequency is very high. I will never hit that frequency when I operate the line, because if I will hit it only if I design the line to do this for me. All right? If I design the line to do this for me, to operate near the resonant frequency, then I design a resonator. And resonators are extremely important in filtering, when you filter frequencies out, or in oscillators. Remember oscillators from your circuits? Do you remember what an oscillator is? It's like a source that provides one clean frequency. An oscillator that provides one clean frequency is nothing else but a transistor that has been matched with a resonator. A transistor and a resonator together create an oscillator. And you need oscillators everywhere. You have them everywhere, here, everywhere. How else are you going to create your frequency? To communicate, you need to create a frequency here, even for Wi-Fi. Wi-Fi, what is it, like 2.5 gigahertz, all right, for Wi-Fi. I need to create on my phone a 2.5 gigahertz wave, voltage, frequency, whatever, all right? How do I do it? Like this. I take a section of a line and then I make it in a way that becomes a resonator. And then I put this resonator, I design it. There is a whole design in high frequency about oscillators. I place this resonator next to a transistor, and the transistor then is creating one single frequency. So it's pushing power into a signal that is moving between positive and negative values every half a period. And it's pushing power. That's what the transistor does. But it's pushing power like harmonically. So in a signal that goes like one frequency. That's what an oscillator does. All right? Have you seen oscilloscopes in the lab? What is an oscilloscope?
You can measure like.
Yes, that wave that your oscillator has developed somewhere and it's coming to you, you detect it with an oscilloscope and you see it and it looks nice if you tune it to the right frequency. All right, so that's what those do. And we are going to see them later, but remember that. So a section of a line that gives you the appropriate L and appropriate C can be designed to become a resonator. And this is what we are using. I mean, if you think, it's very, very simplistic on how we create these circuits. It seems like very complicated. It's not. If you take things down to a simple way of looking at them. Now, this is our expression, and we call it either A up here, and 8 has R and G in there, so it's a full equation, second order differential equation for the voltage for losses. But for the lossless case, it is a second order differential equation without R and G, only with L and C. And for this lossless case, you can prove that there are two possible solutions to this, for this voltage. Two. The second order, you expect two solutions. Is that right? Yes. So the first solution is what we indicate by plus, and it's a voltage. We call that, the name is the incident voltage. So I'll give you also some of the names that you're gonna hear me saying starting on Monday. So this is called the incident voltage. And you will see here why I call it like this.
Wait, what's that base?
I'll show next. And that is called the reflected. For now, you just need to see what is the form that they take. So each of the solutions, which is one, what we call wave, is going to have a real, a constant, like a magnitude, as we say here, and a phase. And the phase comes from this beta z. And there is the reflected wave, as we call it, that has its own amplitude and has its own phase. Same as the incident, but with a different sign. Now, all of these are definitions now. Let's try to see what that means. And then here, going below, I'll show you the value for beta. What is beta? Maybe we can just say here that beta for the lossless case is omega square root of L C. And that is called the phase constant. There are two ways to call it. Propagation constant for lossless, or phase constant, or okay. All right, let's try to understand what those solutions mean to us. So we are going back to the symbolic representation of the line, because that's where we can understand what that means, what those mean. So I'm taking the positive solution. I assume that the positive direction always, these are now all conventions. I'm going to do them so many times that you're going to get used to them. So a convention is, as the line goes from the left, we always have the source on the left. On the right, we have, so the left is the source. The right is what we call the load, all right? So the source is here, and I don't need that. Source is there, and load is here. Left, source, right, load, always meaning. On the left is where we put a generator and create the excitation. On the right, we put whatever else, other circuits, we put anything, passive circuits, active circuits. We call that the load. Okay. Now, if I excite it from the left, then my V plus wave, which I called it the incident, is coming from my source, and it's a wave that goes towards the load. And why it goes towards? Because the negative sign minus J beta Z shows that as I move along the positive Z direction, the phase of this wave changes, becomes more and more negative. Okay? So the phase changes like that. That wave, because it moves from the left to the right, is called the incident wave. The other wave that is moving from the right to the left, because on the right hand I have my load, on the left hand I have my source, it's called the reflected wave. And why do we have that? Because we try to visualize in time, even if there is no time here, it's only frequency. We try to visualize in time what happens. If, for example, I visualize that I have a source, creates a wave, and this wave goes like that, and at some point arrives at the load, and then at the load it sees something and reflects. So then it's going to go back. All right, so it comes like this, finds the load, reflects, and then it goes back. And that is the visualization that people had, and we call them the incident and the reflected wave, even if we don't have time. They look like they move in space, but not in time. There is no time here, all right? We are in the frequency domain. So I told you what beta is when we have no losses. What, however, is in place of beta when we do have losses, when we have R and G. In that case, when we do have losses, so say here with losses, this one changes into minus gamma z, and this changes into gamma z. Where gamma is given by this, and gamma has the value of alpha plus j beta. Beta still is called the propagation or the phase constant. Gamma is called the complex propagation constant in this case. And that all is in your book also. But alpha now, if it exists, when alpha exists here, is called the attenuation constant. Why is alpha called the attenuation constant? Because that's the constant that shows that the wave attenuates, its amplitude goes down as it moves on the line. And why does the wave attenuate? Because there is an absorption. To think there is a loss. To think on how waves attenuate, remember when you throw a pebble on a lake, goes and then creates a little ripple, and how the little ripple is like a wave, all right? That's why you call it wave. And then the amplitude goes down over time. Well, it goes down for two reasons. One reason is because this disperses over an area. The second is because there are losses. I mean, you know, when you, it's like there are losses because there is a mechanical pressure that creates the waves. All right, you know that waves do go down eventually because a wave in the water, how is it created? What do you think? What creates a wave in the sea, in the ocean? What kind of force creates a wave in the ocean? What force?
Like gravity?
No gravity, no, that's other waves are from gravity. When the moon comes close, and there are some, how do they call these waves? Because of the moon comes close to the earth. And tides, thank you. And these are gravity because of the moon. But the other, when you go surfing, is that gravity? No, these are pressure waves. Why? Because there is when the wind, all right, the wind comes with a force, and then it pushes the mass, the water mass. And what does it do when you push mass? Then you create pressure, molecules pressure each other. So it's created because there is a pressure, mechanical force, all right, that forces part of the water to come up and then it goes down. I mean, this creates that kind of a wavy, it's like a mechanical force that creates it. Of course, here, this, and then that's the other thing. When you create a pressure wave, every time you pressure molecules to come together, because the water is not compressible. If you try to compress water, put in a bottle and push it down, it's not going to be compressed, all right? It's going to come out of the sides, but it's not like air. And you can compress air. Water cannot be compressed. So when you push it down, you put the mass down, then there is another place going to come up. That's why the wave goes like that. What happens, however, when you push the mass down, the water mass down? Then you push the molecules down, then you have to push with energy. You put a lot of energy to do that. Have you tried to create, like in the pool, when the kids play and they do the splashing and stuff, and then there is a lot of ripples, water, and is created? You have to do that. You have to spend a lot of energy to splash the water to create these kinds of ripples. You need that. And when you create them, eventually they dissipate. I mean, if you had, for example, an infinite ocean, and you had a constant wind, let's assume that you had a constant a constant tornado in one place, and then creates these huge waves. Eventually, these waves will dissipate because they absorb the energy. That is, the molecules cannot be compressed. So every time you try to do something and push the mass, you're going to lose energy, and eventually it takes out of the energy of the wave, all right? And then it goes down. The same thing happens here. These are electric waves. You create them not because you push any mass, but because you push electrons in the system. That's how you create an electronic wave. You push electrons for some time, and then you pull electrons for some time, all right? So that creates a harmonic wave. And if there are losses in the system, every time you push electrons in there and they scatter, as we discussed, then you're gonna lose power. And then if there is scattering of the free electrons in the conductor, then you have losses that come in the form of R. Or here, if you write it in the form of the wave, they're gonna be in the form of alpha. Excuse me. Sorry.
It's 4 o'clock.
Okay. So these are the expressions that I have here, and that's where we are gonna stop. And what we are gonna do next time, see what I'm gonna do next time? I'm gonna put a load at the end. And now we are gonna start solving problems. This is all of the theory. This is everything you need to know about transmission lines right now to be able to solve problems, no more than that. So these equations, I want you to remember them, this here. There is one more parameter, which we're going to use quite a bit, that is called the characteristic impedance of the line. And the characteristic impedance of the line is nothing else but the ratio of the positive incident voltage divided by the incident current. So look at this, and we are going to come back and do problems on Monday. All right? And we have a problem solving session, so please come with any questions you have. Thank you.
I have a question real quick.
Yes.
So why in your example with the waves? So why again do they like die off over time?
There are two reasons for that. Because one is because they disperse over space. You remember what we saw in cylindrical surfaces for the electric field, that it goes as 1 over rho?
Yeah.
They go like that. And the second, because of losses.
Okay.
Okay.
Also, what did the you mentioned the resonator circuit earlier. What exactly was that supposed to be doing again? I don't think I caught that.
I have to, so here is what I suggest, because there is a waiting another class and we have to leave. Could you come to office hours today?
I'm not sure if I
Can?
Yeah.
Okay, then I have to, well, because I have to leave right now here, the
Okay.
faculty member who is waiting.
All right.
Okay, just email me and I will send you the material.
Okay, thank you.
Apologize.